Hello and welcome to GNA University. My name is Burhan Bashir. I'm an assistant professor in the Department of Mental Radiology and Imaging Technology, School of Allied and Healthcare Sciences. So, continuing our topic with CT instrumentation, today we will be discussing about the first half of the CT instrumentation that's known as imaging system. So let's first try to understand what is the purpose of imaging system. The purpose of imaging system is to produce X-rays, shape and filter the X-ray beam, detect and measure the radiation passing through the cross-section, and then convert the transmitted photons into digital information. Remember that in the very first step, the imaging system does not create an image, but at the end, it only creates measurements, which require further computation and mathematical reconstruction. Then, finally, we can get a cross-sectional image. Now, let's try to understand the workflow that happens in the imaging system. As you are able to see on the screen, the first component is the X-ray tube, which produces the X-rays. Then are the spatializer filters. Most commonly, we use bow type filters, which filter the X-ray beam. Then there is the pre-patient collimator. The pre-patient collimator shapes the X-ray beam according to the slice thickness. Remember, in CT instrumentation, we have two types of collimators. One is known as pre-patient collimator, the other is known as post-patient collimator or pre-detector collimator, as you are able to see here. Here, after the X-ray is produced from the X-ray tube, it goes through the filters, then it is shaped according to the slice thickness by the pre-patient collimator, then it goes into the body of the patient. While it emerges, some of the obliquely traveling photons are absorbed by the post-patient collimator, and it only allows the directly traveling X-ray photons to reach to the detector. The post-patient collimator is important so that the scattered radiation will not be registered on detectors. Then, detector is a specialized device which is capable of creating a measurement from this X-ray photon. And those measurements are further taken away by the detector electrons. So this is the flow diagram of CT imaging system. Let's try to understand these components one by one in detail. So, the major component of the CT imaging system is gantry. Gantry comprises of generator, X-ray tube, filters, collimator, detectors, and detector electronics. As you are able to see from the screen, this is a cross-sectional view of the CT gantry when it's open. Here, you are able to visualize different components. Like on the number 1, you are able to see here, this is the X-ray tube. Remember that the X-ray tube used in CT is more specialized than the one that we use for the diagnostic X-rays, as its operating voltage or kVp starts from the 120 k's. So, for that reason, it needs to be more efficient and more advanced. Followed by this, second thing is the filter and collimator and the reference detectors. The third is known as internal projector. Now, if we work with the X-ray tube on a higher exposure, there is a lot of heat that is being generated. So, we need a cooling device apart from the normal cooling that we use for the X-ray tubes. For that purpose, here is the number 4 that's known as X-ray tube heat exchange oil cooler. Then on the number 5, here you are able to see that this is the high voltage generator that is also present inside the CD gantry. Then the number 6 is direct drive gantry motor. This gantry motor helps the pole gantry to achieve rotations. Number 7, this is the rotation control unit. So this particular electronic device is responsible for controlling the gantry motion. On number 8, here just directly opposite to the LCD tube, these are the detector or the data acquisition systems, which comprises of detectors and detector electronics. So on number 9, you are able to see this is the detector ring. Then on the number 10, you are able to see the slip rings right here. So slip rings are the components which allow for the continuous rotation of the X-ray tube as well as detectors. Then continuing on the electronics present in the CT gantry, on number 11, you are able to see the detector temperature controller. So as the X-ray is continuously falling on the detectors sometimes may heat up. We need to keep a check on the temperature of the detectors also. So this particular electronic set is specialized for that purpose. On number 12, you are seeing the high voltage generator. This high voltage generator is capable of producing a kVp which ranges from 75 to 150 kVs. Then on number 13, you are able to see the power AC to DC unit. And on number 14, you are able to see the line noise filter. So these are some of the electronics and devices which are present inside the gantry of the CT machine. Now, the most important part of the CT gantry is the generator. Generator are high voltage transformer is a device which is responsible for producing a high kV that ranges between 120 to 220 kV peaks. The generator produces high voltage and transmits it to the X-ray tube. The CT scanner now uses high frequency generator, which are small, compact, more efficient than the conventional generators. So this function is required as we need more smaller and smaller components so that all of these electronic devices will be fitted in one single gantry. So these generators are located inside the gantry and the power capacity of these generators are denoted by the kilowatts. The CT generators work on a frequency of 5 to 50 Hz and have a kV range of 30 to 60 kVs. While with these type of high efficiency generators, what kV selection you are able to make is ranging between 80 kVs to 140 kVs, while the MA selection is made from 30 mA to 400 mA. The next important component of the CT imaging system is known as X-ray tube. Earlier or in the older models, we were using oil-cooled fixed anode X-ray tubes, which had a large focal spot which ranged about 2.25 multiplied by 12 mm and had an energy range of 120 kVs and 33 mAs. But now, in the modern day time, we are using the rotating anode X-ray tubes, which are more efficient and have high heat dissipation capabilities, which have a focal spot of 0.6 mm. So, they can dissipate a large heat load, maximum up to 8 mega heat units. This is a diagram of the X-ray tube that we particularly utilize for the CT gantries. Now, the next important component of the imaging system are known as filters. So, filter is used to filter the X-ray beam so that the low energy photons will be absorbed before reaching to the patient. If those low energy photons will reach to the patient, they will increase the patient radiation dose and they will not contribute towards any of the diagnostic information. So, filters are used to filter the radiation beam and protect the patient from the low energy rays and ensure that the beam uniformity for the detectors. So, normally three types of filters are utilized in CT machines. One is known as mathematical filter. The mathematical filter is used in a post-processing technique and it does not interfere with the direct beam. Here, the bone and soft tissue algorithms are utilized to clear out the image of any of the noise. Next is known as inherent filtration. The inherent filtration is utilized by the X-ray tube itself. So, when the X-rays are produced from the anode end, then the low energy photons are absorbed by the anode itself as well as the glass envelope and the surrounding electronics. That is known as inherent filtration. Now, the next is that this inherent filtration is not sufficient alone. We have to use added filtration. For added filtration, the material of choice is aluminum or Teflon, and a special type of filter design that's known as bow tie filter is used. So, filtration increases the mean energy of the beam and the beam becomes harder, which can give rise to the beam hardening artifact. The next component of imaging system is known as collimators. So, collimators are there to define the thickness of the slice, reducing the patient radiation dose and improving the image quality. And in case of CT, we use two types of collimators. One is known as pre-patient collimator, second is known as post-patient collimator. For the pre-patient collimator, it is responsible for defining the size of the focal spot and reduces the penumbra effect onto the patient, while as the post-patient collimator controls the scatter radiation and improves the image quality. This is a block diagram showing the functioning of collimators, the pre-patient collimator, and the post-patient collimator in case of CT. So here you are able to see that this is the X-ray tube which is producing the primary beam, followed by this is the filter. Then after coming up out of the filter, these X-ray beams will be shaped by the pre-patient collimator, and after that they will go into the body of the patient. After leaving from the body of the patient, some of the X-ray photons will be scattered or diverted. Those will be absorbed by the post-patient collimator, and the post-patient collimator will only allow the straight traveling photons to reach to the detectors. Once they reach to the detectors, detectors will generate an electrical signal which will be further forwarded to the detector electronics, which will convert them into the digital signal using a device that's known as ADC. ADC stands for analog to digital converter. Now, this digital data is transmitted to a computer where the image reconstruction takes place and finally a CT image is created. The next part of the CT imaging system is known as detectors. So detectors are responsible for capturing the radiation beam from the patient and convert it into the electrical signal, which are then converted into the binary coded information, and that binary coded information is converted into an image or a cross-sectional image. So there are different types of detectors. Earlier we were using gas-filled or gas ionization detectors, but in the modern day time, we are using scintillation crystals. In the gas ionization detectors, they converted the X-rays directly into the electrical signal, and the gas that we were using was xenon gas. But their efficiency was low, and we cannot reduce the size of these detectors beyond a certain limit. To overcome this problem and to make the machine more efficient, we shifted towards the scintillation crystal detectors, in which the first type that we used was photomultiplier tubes, in which we use rare earth metals like sodium iodide, calcium fluoride, and bismuth germanate. In the modern day CT machines, we are utilizing detectors as photodiodes. Photodiodes are made up of calcium tungstate and rare earth oxide ceramides. In multi-slice CT machines, The detectors are placed in three different designs. One is known as matrix, second is known as adaptive array, and third is known as hybrid. Now, once the detector measures a transmitted photon, the detector electronics or the detector array will convert that measurement or that analog signal into a digital signal, and that will be forwarded to a computer for further processing. That's all for this lecture. We will continue with the second part in the next video. Thank you so much.